So today, hello everybody. Today, our plan is to have this lecture, which is of 40 slides, which may be a little bit shorter than usually, and 2 practical exercises. So somewhat longer day than usually, but it is really nice to get this done today, everything, because one practical exercise will be to generate the signals to be transmitted, and the second practical exercise will be to receive this signal with noise, and this will also help us further in your final course project task, where you will have to make simulation programs. So basically, you will have to use the same receiver we are going to discuss today. And accordingly, you can even merge these 2 practical exercises into a single report. Yes, so basically you can make one report for exercise 3 and 4, or you can make 2 reports, one for exercise 3 and one for exercise 4, if it's more convenient to you like this. So you can choose how is more convenient for you to report these 2 practical exercises, both of them at once, or accordingly each of them separately. Either way will work fine for us. So, as I said, we already discussed the coding part, and now we are going to return to modulation and shift keying. So, as we discussed previously, there are 3 the simplest binary shift keying types. There is amplitude shift keying, there is frequency shift keying, and there is phase shift keying. So now let us discuss how transmitter works for each of these types and how receiver works. So basically the idea is pretty simple. You have some binary data. This is then modulated. So we now get amplitude shift keying signal, for example, which then becomes noisy, somewhat like this, for example, which then needs to be detected. So our purpose is to read what data is hidden in this noisy signal. And we are going to discuss the best way how to do that, the optimum receiver, optimum in a sense that it will make mistake, well, with lowest probability. So we'll start with amplitude shift keying, but all of them will be somewhat similar. Yes, so we are discussing them in their order. First amplitude shift keying, then frequency shift keying, then phase shift keying. And accordingly, the same way it will go for receivers. So amplitude shift keying is accordingly changing the amplitude of the harmonic signal. So this harmonic signal is a carrier wave. So basically, it's like some mean of transporting energy over the distance, carrier. And accordingly, the information itself is hidden in this amplitude. So here we can actually also write that there is a carrier of the specific carrier frequency, F0, but the amplitude of this carrier is 0. So basically this equals to 0 in total, yes? So basically amplitude defines what information is being sent. If we send binary 1 symbol, then we have certain voltage amplitude. If we send binary 0 into a symbol, then the amplitude is 0 volts, yes? And accordingly, this is quite simple, and it's possible to make this modulation type with a single switch, electronic switch, which is controlled by a signal. And also it's nice to know that it is some sort of energy efficiency, yes, because when you transmit 0, you actually don't send any signal. It's just silence period, yes, so you do not waste any energy to generate this 0 signal. However, everything comes at a price, and this is actually the weakest of the modulation types in a sense of error probability, which you already should have known by now, because we discussed the error probability calculation, the difference between different modulation types, and you even had to calculate that in your course project for your specified modulation type. So we'll return to this again later when we'll finish the course project last 6 tasks, because we are going to get noise immunity plots, which are called Bear curves, yes, for each modulation type, which shows accordingly how error probability changes depending on signal to noise ratio. So the stronger is signal, the less probable is error. Here we have logarithmic scale. Log scale, yes, so here we have -1, -2, -3, -4, and so forth, which is degree of the error probability. So for example, 10 at the degree -5 is 1 error in 100,000th symbol, yes, which is just repeating what we already discussed previously. So amplitude shift keying is easy to create, but not so efficient. Its plot looks like somewhat like this, yes, depending on specific data sequence. And accordingly, how can we generate this signal? So we will make this generation of signals on our first practical exercise today and reception on the second, yes. Probably even we will have this lecture go in one go, yes, because it's not so difficult, not so long, and actually, yes, actually at once we will get to the practical exercises after this lecture. So the idea is quite simple. We need to have this switch, which accordingly either turns on or turns off this carrier signal. Yes, so here we have this carrier signal, continuous, uninterrupted, and going as a harmonic wave. And here we have this data signal, which accordingly is as a control signal for our electronic switch. You can use, for example, transistor for this purpose, or rather, even better yet, a field transistor. Yes, and because bipolar transistors, well, they can also operate in cutoff mode. Yes, like if the voltage exceeds certain threshold, then it's open. Otherwise, it's closed. But it needs some resistors and so forth. And field transistors are actually more self-sufficient. Yes, we can use actually a single field transistor, and that's it. If we choose it correctly based on the voltage and so forth, yes. So this is the electronical switch, basically a transistor which opens up each time we have 1 and closes when we have 0. And hence this will actually accordingly let this signal pass and will actually be closed, and then the signal cannot pass. Yes, so this way we actually generate binary amplitude shift keying. Then we need to amplify it before sending it over the distance, because during the propagation of the signal over, for example, few kilometers, as you know, it will lose some of the energy, it will become weaker, it becomes attenuated, and there are also other effects like intersymbol interference, multipath, and so forth, which can make it worse. So it's better to perform some initial signal amplification so that it can go farther and remain stronger. Yes, so that is basically our transmitter for binary amplitude shift keying. This is generator, which accordingly creates carrier wave. So this is carrier generator. Yes, and the modulation, mathematically speaking, can be represented as multiplication of this carrier signal G of t, yes, no, sorry, this S of t. So modulated signal S BASK is then calculated as carrier signal S of t multiplied with information signal U of t, which accordingly also recalls with Fourier transform properties, which one of them was modulation theorem. We have talked about that on one of our first lectures, that there is Fourier transform theorem, that if you multiply two signals, then the spectrums, so here, for example, is one spectrum, here is another spectrum, and one of the signals you are using to multiply is actually harmonic, sine or cosine wave, yes, then the spectrum is being just simply translated, yes, so that will accordingly change the spectrum of this signal by shifting it to this carrier frequency, omega 0, which is 2pf0, yes, so that was Fourier transform property, and accordingly we are just simply using that as a direct approach. Of course, we can actually make a regular multiplication here, and it will work all the same. So we can actually use simple multiplication here. However, for that reason, you will need to make certain that here we have 1 and 0, yes, or u max and 0, yes. This can also work. We can just simply multiply these signals. So the simplest implementation would look like this. Yes, we have transistor, which is open and closed. We have this resistor, which accordingly sets the mode for this transistor. We have our data pulses, and we have our generator. So I didn't plot entire generator here, only its resonance loop, yes, which generates the carrier. And here, as at output, we are going to have then modulated amplitude shift keying signal. Pretty simple and straightforward. You can easily probably make that for yourself if you'd like to try it. Yes, and you will only need a generator, which also comes in the way of ready chips, yes, microschemes, which can be used to generate a signal of desired frequency. So one more thing I'd like to mention, that we actually in generators rarely use this resonance loop, and more often we are resorting to quartz crystal. Yes, for example, even your electronic hand watch, yes, has quartz crystal in it because it's very stable compared to this schematic consisting of two reactive elements which have their losses, which depend on temperature and so forth. And quartz is actually much more stable, meaning that it will generate the frequency of 0 much more precisely, and it will not change as much in time. Because the problem with these generators is that if we desire to have this frequency of 0, this frequency can increase, decrease, and so forth to be unstable. And stability for the quartz is much higher. Quartz can be essentially also described as a model. Yes, so this is not really like what is inside the quartz, because quartz is the piece of the crystal, yes, and basically it has a piezoelectric effect. When we apply some voltage, it changes its shape, and accordingly, if its shape changes, it tries to maintain the same charge on its surface. Yes, so basically this is just a crystal, yes, but we can effectively describe it with this model, which is a simple schematic both for parallel and for series loop, yes, resonance loop. It also, of course, has some loss, and factually it has two resonance frequencies rather than one, but they are so close that we actually consider them to be a single resonance frequency of our desired frequency, and it can be calculated for this model according to this. Yes, so the quartz is just a part of the generator. For the generator, we also need, so here, for example, is the same quartz. For the generator, we also need a feedback network and amplifier to work as a generator. So as you know, amplifier can have feedback network. For example, if we are talking about operational amplifier, yes, then you can, for example, have this type of the schematic, yes, and it will accordingly have a specific amplification ratio, yes, K, depending on these two resistors. Well, basically R1, for example, divided by R2. And this is a feedback, yes, because the signal from the output is returned to the input of this amplifier. Furthermore, this is a so-called negative feedback. This resorts to the phase of the signals, but basically the easiest way to think is that it tries to stop this device from working. Positive feedback accordingly attempts to keep this amplifier going without energy. Yes, so if you imagine that we stopped our signal, then the positive feedback will try and continue operation of this amplifier as long as possible. Well, this is very simplified explanation, but it's like so that it's easier to understand how this works all together. Yes, because this feedback actually will let amplifier to continue generate these frequency signals. Because if we take the signals right open out of this resonance loop, then it will become weaker and weaker because we have loss, and as you know, this means that the signal will accordingly fade. Yes. So we need this amplifier and feedback network to actually reignite this signal. Yes. And that is the idea how it works. So here we have short video explaining the basics of the generators. So let us watch it. So here we have this amplifier. Yes, this is amplifier. Here we have this basically quartz crystal sending wave, yes. And our amplifier has inversion. So basically this means that now the phase is opposite of our signal. Yes, we have opposite phase of our signal. We have the signal stronger, but now it's not a plus sine signal, but a minus sine signal, which we are then using for our purpose, yes, as a carrier signal, but we also send it back at the input of the inverting amplifier. However, in order for this signal to actually be superpositioned with this, we need to invert it again. So basically what is here is another inverter. So let's see how it works. Yes, so yes, we change the phase for P or 180 degrees. And here this feedback network changes it again for 180 degrees so that they are in phase. Yes, so basically we have the same phase. Yes, and basically also it makes the signal weaker as of such, because this feedback network has only passive components such as capacitors, inductors, resistors, and so forth. Yes, so these do not generate a new signal. They can only, change the phase of the signal, and accordingly, there are some losses on these elements, which means that part of the energy will go as a heat at these elements. So effectively, this will reduce the amplitude of our signal. But now it is exactly the same, and the process can repeat all over again, as if without the energy. Yes, so imagine we do not have any energy here, and we only started once this process, and then it's going to keep up supporting itself all over again. However, of course, in real life, you know that we have losses in amplifier, we have losses everywhere. So for that reason, we do need to send this signal as well here. But it, as I said, fades. Yes, so this way we actually, do not let the signal to fade by using this feedback network. So let us continue and see what's inside this feedback network. Yes, because the idea is pretty simple. Yes, we use this signal, invert it again, and basically let it repeat all over again. So that's how this generator is working. So inside this feedback network, there is a simple circuit, yes, which will also be now displayed in more details. So, yes, this feedback network is a circuit, yes, And as amplifier, we can actually again use a transistor, bipolar transistor. Yes, so this is amplifier, and this is feedback network. And of course, we need some power for this amplifier to work as well. So here you can see capacitors and resistors, capacitors and resistors, capacitor and resistor. Yes. So how it's working? Basically, each of these, you can see these are like similar circuits, capacitor and resistor connected in series. Yes. So what happens here is one such circuit will shift phase for 60 degrees and accordingly have some small amplitude decrease, another 60 degrees and another decrease, and last 60 degrees. And accordingly, this gives total 3 times by 60 is 180 degrees. And we have also amplitude loss for each of these small circuits, which goes here. Yes. According to amplifier, again, amplifies everything, inverts it, which again goes all over again. And the cycle repeats itself all over. So that's how this harmonic signal generator actually works. Yes. Which is essential part because this is a carrier signal which we do really need to transmit data. So the idea for amplitude shift keying should be now clear, that we use special generator to generate carrier and an electronic switch which accordingly lets or lets not pass the signal based on your data signal. So a generation is quite simple. This is very similar to coding. Yes, the coding itself is simpler operation than decoding, and well, the demodulation accordingly, detection will be also harder to implement rather than transmitting the signal. So before we go into receivers, let us finish talking about transmitters, and let us see how transmitter for binary frequency shift keying actually works. So the idea there is we use different sub-carriers. So we have this carrier frequency F0, and we have two sub-carriers, F1 and F2. Yes, which are calculated by this frequency deviation or modulation index, which is given to you in your course project as well. And we already discussed how the spectrum of this signal looks like. And we even know, if we recall, that we draw the spectrum as a superposition of two binary amplitude shift keying, like by ASK1 plus BASK2. And it similarly works here. We can consider this to be a single binary amplitude shift keying, the very same which we have discussed here, but there will be two of them operated by the same data signal. So just let me remind you that we need to choose these frequencies F1 and F2 so that the signals S1 and S2, which are these two carrier signals, should be orthogonal. This will give us the smallest probability of the error. Yes, otherwise the error probability will be greater than it could be. So this signal is formed like this. Yes, we have some fragments with one frequency and some fragments with another frequency, depending on what data are we sending, 1 or 0. And if we make this as a superposition of two amplitude shift keying, then it will work like this. Yes, so here we have this data signal. Here we have carrier 1. Here we have carrier 2 with different frequency. And both of them try to go through at the output. Yes. However, we have two switches controlling if the signal will pass or not. The first switch, this switch, will open with positive voltage, plus U. Yes, accordingly, when we have plus U, this switch is opened and the signal passes to the output. However, here we have inverter. Yes, so this will mean that plus U will become 0 at the output. This will not close the switch and this signal cannot pass right now. So if we have plus U. If we have 0 as input here, yes, this will not close this switch, so this will not pass through. 0 here becomes as U, some voltage level, depending on what logic we are using, TTL or some other logics. Yes, it has different voltage levels for 1 and 0. For example, usually we consider that 0 has 0 volts and 1 has, for example, 3 and 3 volts or 5 volts or even more, yes, but it has some specific voltage level for this symbol. So accordingly, this converts to the specific voltage level, which connects this switch, and this signal passes to the output. So at the output, we have either this wave or this wave, yes, depending on what data signal was and which of these two switches was open. And basically, this will work. However, this approach has some not really nice thing that we are using two generators. Yes, it would be very nice if we could somehow have one generator of frequency f0 from which we could then generate f1 and f2 signals, which is completely possible. Yes, we can use frequency divider and frequency multiplier, yes, accordingly, to generate different frequencies from one source. And this will be even nice because in this particular case, each of these generators has own instability. Yes, it also has random initial phase, synchronization problems, and so forth. So it's better to have a single source of the signal, single stable source, which is then somehow manipulated and accordingly produces us 2, even 3 if we'd like to, yes, because with this approach we can actually generate as many signals as we'd like, and only this multiplier changes, yes, and accordingly we can even make this depends on our data. So for example, this will be for symbol 1 and this will be for symbol 0, and there are such so-called frequency synthesizers which accordingly generate different frequency signal depending on the data input. And this is basically already the complete binary frequency shift keying modulator. Now, there is also additional approach that each of these generators, as you know, contains this resonance loop, yes, which has capacity. And we know some semiconductor element also having a capacity which depends on the signal. This is called varicap. Yes. So the idea of this varicap is that it has different capacity depending on the voltage. So here we have some voltage of the varicap, and if this voltage is 1, then the capacity is 1. We change this voltage, this will automatically change also capacity of this varicap. So the idea is quite simple. We add here this varicap, and this way the resonance frequency of this loop actually can be depending on what capacity of this varicap is, and accordingly what is this control signal, data signal. Yes. So this idea is pretty straightforward and simple. We add this varicap into our generator, and this generator itself becomes the frequency shift keying modulator. Yes, we only need to amplify the signal and that's it. This is actually called VCO, voltage controlled oscillator. So you send some voltage at the input of this VCO and it produces the output of a specific frequency. Yes. So this is quite effective and simple way. It also is a single source of signal. We do not have multiple generators. We have single generator with this varicap, which changes the frequency of the output signal. So let us continue to phase shift keying. For phase shift keying, we have different initial phase of our carrier. So for example, for 0, we have plus sine wave, and this accordingly is the same as 0 initial phase, and for one symbol, binary symbol, we have minus sine wave, yes, which accordingly can be described as the initial phase of the P for this sine wave, yes. So these signals are somewhat most different, yes. Of course, it can be not so obvious if we watch on them by the eye. Yes, for example, if we compare difference between these signals of different frequency and difference between these two signals, which only are different in their initial phase, they do not look that different. However, mathematically, this case is the most different signal, which accordingly gives the best noise immunity to this modulation type. Actually, this is actually the best noise immunity signal. All the other modulation types we are using today usually have some trade-offs, and basically for that reason noise immunity is not as good as here. For that reason sometimes NASA has to rely on this modulation type when making transmission of some pictures from very, very far planets, yes, from their space ships. Oh, well, not really ships like we imagine that, but this is still some automated ship which flies to set course and sends us pictures from different planets. Yes, and the distance is so great that we have to use the strongest possible signal, the most noise immune signal, use very slow data transmission rate, use a lot of error correction coding and so forth, just to get that picture, to see what is that planet, yes, how it looks like. So yes, and for that reason we often there use binary phase shift keying as the most noise immune. Yes, it is one of the slowest modulation types, but it is reliable, and reliability in that task, in that purpose, is more important than speed. Yes. So the signal then looks like these phase changes. Yes. So basically, the information are we sending 1 or 0 is hidden in this change of the sine wave phase, and accordingly we will have to design some receiver which will be able to read this information from this received signal. But before that, let us see how we generate this signal. So the idea is also pretty straightforward. We have a single source because we have these signals of the same frequency. Yes, so we have F1, F0 frequency here actually, and here also we can have the same frequency, because for phase shift keying the frequency is the same. Yes, we do not use different frequencies. So here we have F0, F0, and F0. I will change these indexes in the final version, which will be uploaded in Ortus. There is already a version in Ortus, but it's currently the same as here. But I will change that to not to confuse you further. Yes. So that's why we have a single generator, and similar as to frequency shift keying approach, we use two switches now, two electronical switches, which accordingly are controlled with the same signal. Only thing is that first signal is a switch controlled with direct signal, and the second switch is controlled with inverted signal. Also, we need to invert the sine wave. So here we should have the sine wave, and here we should have the opposite phase sine wave. Yes, for that reason we invert also a sine wave. This is not a not element. It's displayed as not element, but actually it's more like sooner like inverting amplifier with ratio k1, so that it doesn't actually amplify its amplitude, it only changes its phase. Yes, and then accordingly we open one of these switches at a time, and the corresponding signal goes straight to the output. That's the simple way how to make it. However, it's still too complicated structure, yes, and we can make it easier. It would be much easier if we convert our data signal into NRZ format, which now has plus and minus 1, and straightforward multiply it with our sine wave. So this way, if we have here sine, we multiply it with plus minus 1. Here we are going to get plus minus sin, depending on what data was. If we have 1, it will be minus. If we have 0, it will be plus. Yes, and that's basically exactly what we wanted to do. We wanted to change the sign of this harmonic wave. Yes, all that's left is just to amplify the signal and send it to antenna and further, yes, to the receiver. So this distance between signals is what's important that affects the error probability. So let us talk a little bit about it. You already have had part of this material when we were discussing the formulas which can be used to calculate bit error rate, BER, or how we mark it in our software, in MATLAB or Octave, like PR, error probability, yes? And you had a formula like 1 minus phi function of certain noise, signal to noise ratio. Well, basically here we had a square root, for example, and signal to noise ratio. Sorry, signal to noise, like this, for binary phase shift keying, for example, yes? And basically for amplitude shift keying, we had slightly different formula. Well, actually, now let us maybe see that. I can open course project tasks and guidelines. Yes, and there we also had these same formulas. Here are they, yes. So this is for phase shift keying, we have 2 here. This is for amplitude shift keying, we have 2 at the denominator. And for frequency shift keying, we don't even have these 2 anywhere, yes. So this is affected by the distance between these signals. We already probably showed you geometrical representation that we, for example, for amplitude shift keying, draw it like one signal is 0, one signal is as a vector. For frequency shift keying, these are orthogonal vectors, so the distance is greater than here. Yes. And for phase shift keying, these are opposite phase signals, and the distance is even greater. So in fact, this is the maximum possible distance. If you rotate these vectors any other way, for example, like this, so the distance will actually decrease. Yes, so this is maximum possible distance we can get. And this is somewhat best for us if we use orthogonal signals. However, at the same time, this distance can be calculated as a formula. Yes, so we can do that mathematically by calculating this integral between the difference of these 2 signals, S1 and S2. Yes, so square of this difference, because it can go positive, it can go negative, yes. So we need to actually consider that it contributes regardless of the sign, because it can happen, like, for example, in some fragment here, we are going to have this signal as a negative, yes, because we multiplied them different. We have the negative, negative here, then have a lot of positive, and somehow this will cancel out some of these positives value, and total distance will become smaller than it could be. So for that reason, we are using, say, here a square to get rid of this sign and always count this difference. Yes. Now we integrate this over the duration of the signal, usually 1 period, for example, of the harmonic wave. Yes, and define this distance. So the greater is this distance, the better. Yes, because otherwise noise will have to how to say it, corrupt the signal stronger, because we need to confuse one signal for another, and if these signals are very different, the noise has to do a lot more work to actually achieve this confusion. Yes, of course, nothing is like intelligent here. Noise doesn't have intelligence and doesn't even have this purpose. It just exists and is added to our signal. This is just the thing we have to account for. But, well, basically, if we're talking in these terms, there must be more noise for longer distance to actually confuse one signal for another. so that we send signal S1, and there has to be a lot of noise so that we actually receive this signal as S2, yes, and consider that in fact it was transmitted as S2. However, it is an error, yes. And if the distance is greater, then we must have more and more this noise to actually for this to happen, yes. You already discovered that during your first practical exercise when we had unipolar pulses, 5 and 0 amplitude, and where we had NRZ signal. There we had greater distance, and accordingly you had to reduce signal to noise ratio in order to get the same amount of errors. So it's like this also here. So what we are going to do here is now open these brackets, yes. So here we have first signal squared, second signal squared, and this a mutual multiplication of these two signals, yes. Also, we can separate this single integral of these three values into three integrals, yes, like integral 1 for A, plus integral 2 for B, and plus integral 3 for C. Yes, this is the property of the integrals, and we are going to do just that. So here we have one integral, here we have second integral, and here we have this third integral. And actually, if we look closer to this integral, this is actually the energy of the signal. Yes, and this is also energy of the signal. So if these signals S1 and S2 has the same amplitude, which is usually so for frequency and phase shift keying, not for amplitude shift keying, of course, because for amplitude shift keying S2 is just 0, and accordingly energy is also 0. We have discussed that it's nice that it preserves some of the energy. Yes. But for frequency and phase shift keying, we usually choose the same amplitude, so these two energies will be the same, just E. Yes. And we can actually denote them as energy E. So the question is now with this part. Yes, what is actually here? This double initial or this double mutual multiplication. So it depends on the modulation type, of course. And actually, this is the shared energy of these two signals, what energy they have in common. And for that reason, and that reason alone, we prefer to use orthogonal signals for binary frequency shift keying, because for binary frequency shift keying, these two signals have different frequency. So multiplication of different signals, different frequency signals, F1 and F2 signals, yes, not really frequency multiplication, but multiplication of the signals with these frequencies will produce intermodulation components. Yes, as you remember, it will produce not only F1 and F2, but it will also produce frequency F1 plus minus F2. It will produce double F1, double F2. So these all harmonics are also produced because of this multiplication. So for that reason, we prefer it to have a 0, yes, for frequency shift keying. And that is 0 only if these signals are orthogonal. That's actually the property of orthogonal signals, that this scalar multiplication or mutual correlation is also the same, yes, is 0. So this is the property. So for binary frequency shift keying, this accordingly means that here we will have just 0, and we are going to have under the square root just simple 2e for binary frequency shift keying. Yes, for binary amplitude shift keying, we are going to have here square root. So this is E, this is 0 because S2 is 0, and this is 0 because S2 is 0. So basically we are going to have simple E. And for binary, this was frequency, and for binary phase shift keying, as you imagine, we will have twice as more than for binary phase shift keying, because S1 and S2 are actually interchangeable. Like, let me actually write it like S2 is actually minus S1. Yes, so if we put minus S1 here, here we have double, minus and minus gives us plus, and we actually have like 2 energy here, yes, extra, which will give us this, what is added in comparison to here. So far it looks like we are actually getting this part, yes. Sorry, where did it go? Ah, okay. This part, yes. Well, the only thing is that actually in these formulas we had everything twice smaller. Like here we had like this. Accordingly, here we had just E, and here we had 2. This actually is more a result that we divided like this distance, yes, for example, for amplitude shift keying, and noise is also double, yes, so like this. So for frequency shift keying, here we had for no, sorry. Yes, like this. For amplitude shift keying, we had simple E. Here we had divided by double noise. And for frequency shift keying, here we had 2. So that shortens out and we get this. And for phase shift keying, here we had 4. That gets shortened out, and here we get 2. Yes, so basically this is actually a distance inside this formula. And that's why these three formulas are a little bit different. So this mutual energy is then very important for us further to actually receive the signal. We will use the same approach to receive the signal, but for now, it's depending on the modulation type, can be 0, can be 1, and -1. Yes, so for orthogonal signals, which is cases of binary frequency shift keying, it is 0. For binary phase shift keying, it is -1. And this case is not really interesting for us because these signals are no different. Yes, it's actually the same signal. So if the signals are the same, then this correlation is 1. And this will be important for us further, yes, when we'll actually try compute this S1 and S1. That will be done later on purpose. So this is basically receiver. How operates receiver? Yes, we will use that in receiver. So for that reason, we can express this distance through this correlation coefficient. And this way we get this distance for different modulation types like this. Yes, if we put accordingly here for this distance for amplitude shift keying, for binary shift keying, and for binary frequency shift keying, and for binary phase shift keying, corresponding values in these formulas. So that's the distance, and here is again the geometrical representation of this distance for different modulation types. For frequency shift keying, we have orthogonal signals, which are accordingly displayed as orthogonal vectors, having this p divided by 2 angle between them. For amplitude shift keying, one of the signals is 0, and for phase shift keying, these are in opposite directions. Yes. And this gives the maximum possible distance for these 2 vectors and signals, which are represented by these vectors. So this way, we actually get these error probability functions, yes, which you already are familiar with and probably used for your course project. And accordingly, we can plot these functions as lines on the plots, on the figures, yes, and accordingly that will be the task for you to do with your course project for your specified modulation type, for your specified type of coding. Instead of drawing different modulation types, however, you will draw 2 lines, one with coding and one without coding, yes. So basically one will be coded, one will be uncoded. But we'll get to that on our last lecture after 2 weeks. So basically we have 2 more weeks to finish our course, and everything seems to be going according to plan. So no extra time will be needed. We'll get everything done just in time. So I think we can finish it up without small break. Then we'll make a little bit longer break because we only have 10 slides remaining, and then we'll get to practical exercises with Mr. Chen. So let us then at once talk with optimal correlation receiver, which we'll make in our second practical exercise today, and how it works. So the optimal receiver must select correct signal. So basically what happens during transmission is that there are options like transmitter can send either of these S1 or S2. Then it is transmitted in channel as some selection U, which happens to be this randomly selected signal, yes, either 1 or 2, so Si plus noise. Yes, and we already discussed that we use particularly Huffman and Shannon-Fano coding to get as equal probability of symbol 1 and symbol 0 as possible. So basically we desire to have 50-50% of these symbols, yes, and for that reason the selection of 1 or 0 looks like almost random for the system, yes, and accordingly we can have with 50% probability each of them, and we add noise. So then receiver's task is actually to find out, is it S1 or is it S2? But because of the noise, this is not as simple. Well, let me actually show you an example. Consider that we have S1 of this shape, and consider that we have S2, for example, of this shape. Then transmitting into the channel and adding the noise led us to the signal with this shape. And now you need to tell me, what is this? Is this S1 or is this S2? How to be certain? Well, actually what you are doing, you are, well, as a person, yes, your thinking logic, you are taking this signal, you compare them, have some comparison score, yes, for example, these signals are similar, like, I don't know, in percentage. Well, let's say around 60%, maybe, yes, for example. It's not really important right now. Of course, mathematically, we can calculate precisely this score, yes, and that is what we are going to actually do. Then you take the same signal again, compare it with this signal, calculate the similarity score, and let us say that this was, well, in your thirds, for example, 75% similarity. Then you see that this is more likely to be this signal, so you are trying to detect it as signal S2. So that is our conclusion, that is higher probability that it's signal S2 rather than signal S1. We are, of course, not certain about this, yes, but neither can be certain a receiver, yes, because of noise, because errors can still happen, and for that reason we added error correcting code so that it will handle these errors if they happen. And in fact, the receiver is going to work in a very similar way. All that it needs is some mathematics of how to calculate this similarity, yes, and actually I already told you that it is called correlation. So we are going to calculate correlation between a received signal and one of the possible signals. So basically we calculate correlation between received signals. So I will denote it like this: correlation between received signal with noise and signal S1. And we calculate correlation between received signal and signal S2. Whichever correlation will be higher, that signal was meant to be sent. Yes, so the logic is pretty simple and straightforward. So we only need to find out how to calculate this correlation, and that's it. Yes, so that's how optimal receiver works. Actually, it's called optimal correlation receiver for that reason, because it calculates correlation. And there is also optimal matched filtering receiver, which we'll discuss next week. And we'll have actually one more practical exercise next week, yes, as well. And that will be related to optimal correlation receivers. So optimal correlation receiver actually, of course, isn't always right, but it has maximum probability of correctly guessing what the signal was. Yes, so the probability of well, failure, let us say so, is the smallest possible compared to other types of receivers. Because, of course, there are non-optimal receivers as well. Yes, and in fact, we already tried them. We tried to compare with some threshold our pulse signals, as we imagined. Yes, we tried to use averaging in our second practical exercise. Those were actually also types of receiver. Yes, but calculating the correlation gives the best result. Yes, so let's see how it works. Here, for example, we have received some noisy signal, this signal. Yes, here we have a 0 level, and here we have two clear signals. So basically, we are talking about binary phase shift keying signals, which can be accordingly either +1 or -1, for example. Yes, and we have received some signal value, which is neither +1, neither -1, which is, in our particular case, somewhere around 0.3, plus 0.3. So what we are going to do is we find the distance between first signal, we find the distance between the second signal, and obviously we are going to prefer the signal which is closer to our received signal. Yes, so we have these references, these original signals, and we have these received signals, which is accordingly noisy version of one of these references, because nothing other could have happened. We are sending either +1 or -1. We are not sending -2, we are not sending -3 or +3. Yes, only one of these two cases is possible, and for that reason we compare what we have received with these two cases. So here you can look in more mathematical details about how this works. Yes, these correlation integrals we are now going to discuss. If you are interested, you are welcome to study it. And in fact, it is also discussing non-binary modulation types, which we'll also do later on our last lecture. But for now, we are sticking to these simpler cases like binary amplitude shift keying, binary frequency shift keying, and binary phase shift keying. So the idea is simple, right? We calculate correlation and compare these results of correlation, and then we choose the signal with higher correlation. Yes, there, as I said, there are two methods, correlation receiver and matched filter receiver, which are both equally effective. Yes. So when I told you that optimal correlation receiver is actually the best possible, well, it's not really maybe exactly true, but it still gives the best result. That is true. And matched filter receiver gives the same good result as correlation receivers. And in fact, when we will discuss that in the next lecture, you will see that matched filter receivers is actually correlation too, because filtering procedure actually calculates very similar formula as correlation. Not exactly same, but still very similar, so that we can reduce this to correlation. So in fact, they are both calculating the same correlation. So how does optimal correlation receiver works? It calculates this distance, the difference between received signal and one of the reference signals. Yes. So possible transmitted signals. And for amplitude shift keying, for example, these reference signals, one signal is 0, another signal is sine wave. So what we have received is compared with this, and the higher score accordingly wins, yes, and this means that that signal was sent. Of course, for this correlation receiver, we need to know what possible signals can be. So we need to know the frequencies of the binary frequency shift keying signals, the amplitudes of these signals, and so forth. So these signals must be known. Luckily, of course, it is we who choose these signals, so of course we know them, and we can make our receiver accordingly by using this knowledge. So what we need to do is to calculate this correlation integral for received signal. So this is received signal, and for reference signal. So we need to calculate this correlation integral for each reference signal. We are now having a binary shift keying, so that means we have two signals. One signal S1 for symbol 1, and one signal S2 for symbol 0. Yes, so that means that we have to calculate two correlation integrals, one for signal S1 and second for signal S2. If we are having non-binary modulation type, for example, 16 signals, then we will have to calculate 16 correlation integrals. Well, at least following this logic. A little bit later, I will show you that actually it will be possible to avoid so much calculations and stick to minimum correlations calculated. So noisy received signal is actually the same signal. Well, actually, let us denote it as J because this choice is random, yes, and accordingly noise. So we need to calculate it. As I said, for each possible signal, we calculate this correlation integral. So we need to have generators generating these reference signals. We need to have received signals multiplied with these generated signals. So that is multiplication part of this formula. So each of these blocks calculates this multiplication between received signal and the reference signal. Then we need to calculate integral. Then we need to subtract half of the energy because, well, in general, these signals S1 and signal S2, S3, S4, and so forth up to Sm can have different energy. Yes, so if energy of this signal is different, then we need to normalize them because the signal otherwise will be always positive. Yes, for example, like this. And we need to set them centered across this zero axis so that it will make it easier for us to make this decision. Well, for us, in our particular case, we have signal energies E1 and E2 for frequency shift keying and phase shift keying equal. So for these two modulation types, we can actually skip this part. Yes, do not do that and just make a decision at once. For amplitude shift keying, we'll see that it's a very specific case because one of the signals is actually 0. So we do not even need to calculate all of that at all because it's pointless. Yes, whatever signal we have received here, the integral is always going to be equal to 0 regardless of the signal. So this is pointless to calculate this integral, second integral. The first integral, however, needs to be calculated. Yes. So since we started talking about amplitude shift keying, let us see this structure of the receiver in total. So as I said, only one correlation integral needs to be calculated because the second correlation integral is 0, regardless of the input. Yes. So we calculate this correlation integral by multiplying our received signal with carrier, integrating it, and then reading result after the end of the integration. So basically, if I plot some diagrams here I'm going to have this noisy version of the signal. Here I'm going to have this carrier, Here I'm going to have some kind of multiplication of this carrier. Well, not maybe like this, but like, for example, like this. After integrating, I'm going to get some sort of this line, yes, and I'm interested only in last point, the time when we have completed entire signal, because everything that's happened in between is not yet complete, yes, so for that reason we are interested only in this point, so we are reading that when integration process is finished, the result is read from this integrator by this switch, yes, and then switch again turns off. In addition, of course, here comes all this synchronization, all these clock problems we were talking about. We need to actually have carrier of the correct initial phase, so it should start with specific 0, for example, here. Yes, so for that reason, we need this circuit which recovers the carrier with correct initial phase and helps this generator to generate correct carrier. We also need clock recovery, so sampling, the synchronization of this symbol duration, yes, because this actually tells us how long do we need to integrate. This is the limit of this integral, yes, so it goes here, and accordingly it's quite important to integrate over the correct duration of time. We do not want to integrate smaller than we need to, because this will give us smaller value. Yes, you can see that we didn't achieve maximum value, and neither we want to over integrate, because otherwise we are going to take from the next symbol its part of value. Yes, so for that reason it's quite important to correctly evaluate this time interval, and it also affects when we are going to read the decision. So, as I said, we only need one correlator integral, and this correlation integral, depending on what signal is it, can give different results. So, if we calculate this correlation integral for the reference signal S1, which is harmonic signal, this signal, yes, and it turns out that U is also signal S1 plus noise, yes, so then we are going to have energy of the signal, because if U is S1 and this is S1, then we are going to calculate integral for S1 squared, which is in fact energy. Of course, this energy will be reduced by this noise, but still it will be closer to energy than to 0. Now, if the signal being transmitted was S2 plus noise, then putting here S2, which is 0, will give result of integral as 0. So the result of this integral, if we are talking without noise, so consider that right now we do not have any noise. So if U is going to be S1, the result of integration will be energy. If U is going to be S2, result of integration is going to be 0. And the second integral, regardless of what is U, will always be 0. Yes, if it is S1, it's 0. If it is S2, it's 0, because this S2 is 0. Yes, so we don't even calculate it. Instead, we are going to make decision based on that. Now, if we have noise, of course, we are not going to get precisely energy here, neither precisely 0 here. But still, we can make this threshold between 0 and energy, a half of the energy. That is our decision boundary. Yeah, so for example, if the correlation integral results was like this, we can see that it exceeds this threshold, and it's actually 1. If this correlation is not exceeding, like this, for example, we decide that it is 0. That's as simple as that. Yes, so this decision element actually compares the voltage of this correlator with half of the energy of the signal. And if it exceeds, then it's 1. If it's below, then it's 0. That's just as simple as that. So, for frequency shift keying, we have to use two correlation integrals Yes. In the same way, we still need carrier recovery, still need clock recovery, as it's affecting our integral and reading this integral as well. In our modulation, in our simulation programs, we do not care about that because everything is fine. There is no delay and so forth. There is no transmission actually happening over distance. Yes. So for that reason, in our simulator programs in Octave, we do not really care for that. But in real devices, in real communication systems, of course, this has to be done, of course, yes. So it works pretty simple, exactly as for amplitude shift keying. So we calculate correlation integral, for the second signal, and instead of comparing with some threshold, now we compare these two correlation integrals, I1 and I2. Yes, so whichever of them is greater is that symbol. So consider, for example, that S1 matches symbol 1 and S2 matches symbol 0. Then, if integral 1 is greater, then that was the signal S1, and accordingly that means that we sent 1. Otherwise, it will be 0. Yes, so pretty simple as that. And these correlation integrals neither can be equal as well. Well, they can be equal only if the noise is very strong and actually there is nothing left of our signal. We only have noise, yes, just as strong, so that signal is lost completely in that noise. In that case, it doesn't really matter whichever you choose, it will be an error regardless, yes. Of course, it can luckily choose correct one and there will be no error, but this is sheer luck, yes, and we do not want to depend on this luck in our communication system. That just means that the channel is unusable for communication, yes. And finally, for binary phase shift keying, we also use only one correlation integral, mainly because S1 is equal minus S2. Yes, so for that reason, if we calculate this integral, then this integral, it's actually the same. Well, here we have dt also, yes. It's actually the same integral in both cases, yes, because I can write it like this, S1. Yes, changing the sign before integral, and it's still the same integral. So again, no point in calculating two integrals. And accordingly, in this case, the result, if ut is S1, is going to be plus energy. If ut is S2, then we are going to get minus energy. So accordingly, the same way, we now define threshold. Here we have energy, here we have minus energy, here we have 0, and accordingly, correlation result is going to be like, sorry, didn't want to draw it like in minus, like this, yes. And of course, we are going to have some noise, yes, but still we need to decide in these reading time intervals, is it above 0 or below 0? So that's decision-making element, and it accordingly is 1 or 0. So this is for lecture part. Now I think we can make a short break, and wait, there was last one slide. Well, yes, this explains exactly that what I meant. So for the first correlation integral, here we have either plus energy or minus energy, depending on the signal S1 or S2. And here, accordingly, the same way, we're going to get either minus energy or plus energy. So they are essentially the same. They only differ by the sign. So for that reason, we choose to use only one integral. Yes. So, as I said, now that lecture part is over. And then Mr. Chen will now show you two practical exercises. Well, we will make short breaks between these practical exercises as they will be a bit long. Yes, maybe it may take time. So yes, now we are going to have a break of 18 minutes. So at 9:15 50, Mr. Chen will take over and will start teaching you practical exercise, how to first design these transmitters, and then on the second part, receivers. Yes, so if you have any questions, you are, as always welcome to ask them. But otherwise, after break, Mr. Chen will start practical exercises. Thank you, and probably then I will see you next week.